In 41 through 49, let x and y be sets. Let a and b be any subsets of x, and let c and d be any subsets of y. Determine which of the properties are true for every function f from x to y, and which are false for at least one function f from x to y. Justify your answers. Now, this is an if-then statement. It says if a is a subset of b, then capital F of a is a subset of capital F of b. Here I have the set builder notation for what these sets are defined as. Capital F of a represents all of the outputs in the codomain where the inputs correspond to elements of the subset A. Capital F of B represents all of the outputs, capital F of B, that are in the codomain, such that the inputs come from the set B. This is saying that if the elements in our domain from A are also elements in our domain from B, then the corresponding y values of A are also going to be corresponding y values of B. And that is true. It's hard to draw this pictorially, so to show you that it's true, we're going to prove it. Now, this is one way of going about these sorts of statements. The hardest part about this is first figuring out whether or not this is true or false. And you can try a couple times. You'll notice that it works. That's one way you can approach this. Or you can just try to prove it. And if the statement is false, then you're never going to be able to prove it because you can't prove false statements. So let's try to prove this. Now, this is an if-then statement. There are a couple of approaches to if-then statements, but in this case, I think we should focus on the simplest way, which is the direct proof, where we assume the if part. So we'll start our proof by saying, assume A is a subset of B. So we get to have this property for free. We get to assume that A is a subset of B throughout this entire proof. This will be important for later on. Now, our goal is to prove the then part. We have to somehow conclude this at the bottom, that capital F of A is a subset of capital F of B. Now, these are subset relations here. Subsets relate sets. So this capital F of A here is a set, and this capital F of B here is a set, and they're defined using these set builder notations here. We need to prove that this set is a subset of that set. To do this, we're going to use an element argument, where we start with an element from the first set, and then we show deductively that that element is also, in fact, a member of the other set. Now, normally, we choose elements like lowercase x here. The problem is that x really looks like an element from capital X, and that's not what we're saying here. We're saying that this thing has to be an element of capital F of A, and that's where we go to the function notation. If you notice here, on the left side of this vertical line, we have a representation of what these elements in the set looks like. So this capital F of A here, which is an element of our universal domain of discourse, shows us exactly what the elements of this set look like. They look like this F of A, where A is an element of the set. Now, I'm not going to use the same lowercase a here, because we might just, even though it doesn't really matter since this lowercase a is a local variable to this set builder notation, instead, I'm going to say capital F of U. So assume capital F of U is an element of capital F of A. This is a set, and this is an element in that set. So F of A is the set of all outputs corresponding to the set A, and capital F of U represents just one of those outputs. So the set is the collection of all of the outputs, and F of U is just one of those outputs from that set. So capital F of U is an element. It's an output rather than a set. We need to show that this element is also in capital F of B. But to show that an element is in capital F of B, we need to show that that element can be written as capital F of some letter, which we currently have that, but we need to show that the corresponding input comes from the set B. To do that, let's unpack this definition. What does it mean to be an element of this set? Well, then that means that F of U, number one, is in our codomain. It's an element in Y. And we also know that the input corresponds to the set capital A. So lowercase u comes from capital A. That means that lowercase u is also an element of B. So if A is a subset of B and lowercase u is an element of A, then by definition of a subset, this element U must be an element of B. But now we know that this input here actually corresponds to an element from B, which is precisely the property that needs to be satisfied in order for an element to be in capital F of B. So by showing that U is an element of B, then that means this input, well, really this input here, U, comes from the set B, which is exactly what needs to be satisfied according to the set builder notation in order to be an element of F of B. So this means then that capital F of U is an element of capital F of B. And that's enough to show that capital F of A is a subset of capital F of B. Remember that in element arguments, we start with an arbitrary element from the first set, and then we try to conclude that that element is also an element of the other set, which means since capital F of U is arbitrary, we don't know what U is. All we know is that U started in the set A, and then we proved that it was in the set B, which then it satisfies the property that would need to be satisfied according to the set builder notation to be an element of capital F of B. So this means that all elements of capital F of A are also elements of capital F of B. And so that proves that this statement is true. Thanks everyone, and I'll see you in the next video.